Good morning again. Today we will be talking about discrete probability distributions. Okay, we will talk about the probability distributions of discrete random variables. Okay, so discrete random variables. What is a random variable? If you remember, random variable is a number, is a real number, which will represent the outcome of an experiment, but the outcome of an experiment should be converted to a real number. Okay, number of passes in a soccer game, number of students in a classroom, number of people passing by, number of defective parts. Okay, all these things are random variables, and random variables can be discrete and continuous, as we mentioned before, or they can be mixed random variables. In a random variable, they might be discrete and continuous parts. Okay, probability distribution, again, very easy, guys. Okay, it defines the probability of its unknown values. Okay, so I have the possible outcomes. Okay, possible outcome x1, x2, x3, x4, and then each one will have a different probability. Or for continuous random variables, I may have such a distribution. Okay, I won't have discrete like 0, 1, 2, 3, but this time I will have all possible outcomes, and then each possible outcome will have a kind of probability, but the probability distribution will be continuous. It's not going to be discrete like this one, but it's going to be continuous. Okay, again, this is probability distribution. We will call it probability distribution function, probability density function. Okay, probability density function. Here, we talked about that probability mass function. Okay, what's the difference between probability mass function and probability density function? One of them is for discrete, the other one is for continuous random variables. Okay, so if you remember, it's a kind of bell shape right now. We will call this normal distribution, for example. Okay, and for example, it's about the distribution of the grades in an exam. Some people will get, for example, the average of the grades is going to be like 50. There will be some people who are getting 0 and 5, 1 or 2, something like that. Some people will get 100, but most people will get an average of 50, for example, or 60. So it's something that we are really used to seeing, especially normal distribution, Gaussian distribution. Okay, so in terms of this probability distributions, now we will be focusing on special distributions. Okay, it's not going to be any random experiment and random variables, but this time I will mainly focus on these 5 distributions in this course. They are like Bernoulli distribution, binomial distribution, geometric distribution, Pascal distribution, and Poisson distribution. Okay, what does that mean? They have a special distribution. They have a special characteristic for the random process. Okay, special characteristics for the random experiment. Okay, random experiment, and the random variable will also be related to that. Okay, so for example, if I flip a coin, what are the possible outcomes? They are heads or tails, right? If I choose a person from a class, it's boy or girl. If I look at the outcomes of an exam, for example, pass, fail. Okay, if I check the parts, defective, non-defective. If I check the person, normal, disease. Okay, there are two options. Always there are two options. One of the options is going to be like represented by 0. The other option will be represented by 1. Okay, so binomial is something different, but it has its own special characteristics. Now we are going to choose something. In another distribution type, we are going to say, I'm going to flip the coin and wait until 5 heads will come. How many flips should I have? Okay. In another one, we are going to have a certain period of time. Let's say in 1 hour, how many people are entering the shop? Okay. That's going to be the example for Poisson distribution, for example. So there will be different random experiment characteristics. Each of them will correspond to a different distribution. Okay, guys, this is very important. So different random experiment characteristics, like flipping a coin and seeing what's the outcome, what the outcome is. Flipping a coin and counting the number of heads out of this, let's say 10 flips. And then like flipping a coin until you get 3 heads. Kind of different type of experiments, okay? And they are highly related to real life examples. So that's gonna be the main idea for today's session. For example, let's look at Bernoulli distribution. I'm not gonna go into too much detail. What is P? What is 1 minus P? P is the probability of the random variable x equals 1. Okay, for example, this is success, this is failure, this is normal, this is disease. Okay, diseased person. This is, let's say again, normal, this is defective. Okay, male, female. So all of them are like binary situations, like 0 or 1, failure, success. So one of them has a probability. For example, I have a classroom and 30% of the classroom is comprised of female students. Then the probability of male students will be 0.70. The probability of female students will be 0.3, right? So, and this is the PMF. PMF shows me the random possible random variable outcomes and its probability. Okay, so this was the thing that we discussed, and we now know what it means. Okay, it's called Bernoulli distribution. It's a mathematician. This name is coming from that mathematician. So and we represented like this random variable is distributed according to Bernoulli distribution with a probability of 1 being P. Okay, so let me write this. X is a random variable. Okay, random variable which is distributed according to Bernoulli distribution, whose probability for success is P. Okay, so that's a kind of representation. We will use the same thing. We will change this Bernoulli to binomial, to Poisson, to geometric distribution, and this part will only change with some other parameters if there are other parameters. Okay, so let's move on to the binomial distribution, because in Bernoulli distribution we have this concept, but now we're going to build this binomial distribution on top of it. Okay, if for binomial distribution I have a coin whose probability is P, and it is between 0 and 1. I toss the coin n times and define X to be the total number of heads that I observe. You remember we did this, right? We flipped the coin 3 times, flipping the coin. And what are the possible outcomes? 3 heads, head, head, tail, head, tail, head, and head, tail, tail, tail, tail, tail, tail, tail, heads, tail, heads, tails, and tails, heads, heads, right? So there are 3 heads here, 2 heads here, 2 heads here, 1 head here, 2 heads here, 1 heads here, 1 heads here, 0 heads here. And last time we plotted the PMF of this. For 0, I have 1, 0 out of 8 possible outcomes. So 1 over 8 is the probability of obtaining 0 heads. What's the probability of obtaining 1 heads? It is 1, 2, and 3. 3 over 8. Out of 8 possible outcomes, 3 outcomes will give me 1. Okay. Again, for 2, it's like 1, 2, and 3. 3 over 8. It's going to be 2 heads. And the final one is going to be, again, 3 heads, which is the probability is 1 over 8. Okay. So that is my PMF and also probability distribution. Okay. Probability distribution of each possible outcome, 0, 1, 2, and 3. Are there any possible outcomes for the number of heads? No. I'm flipping the coin 3 times. It either I either have no heads or 1 heads, 2 heads, or 3 heads, right? These are the possible outcomes. What is their probability? 1 over 8, 3 over 8, 3 over 8, 1 over 8. So I can find them by plotting them. But how about if I toss the coin 100 times and I want to plot the probabilities? How can I do that? Okay, that's why the probability distribution formulations will have a generic characteristics. Okay, generic formulas. We will have generic formulas. What does how were we doing? What was the probability formula for that? If you remember, like K heads, like I flip the coin n times, and then n out of K, okay, P is going to be the number of heads. P is going to be the probability of obtaining heads. It's going to be like K heads and 1 minus P to the power n minus K, right? This is heads, and this is tails probability. I have K heads because it says total number of heads, and here I say number of heads. Okay. For example, I have 1 head, 0 heads. Okay, this can be 0, 1, 2, 3, anything like that. This is the number of times. This is number of times I flip the coin. Okay, number of times I flip the coin. But this one, number of heads, right? Number of heads. So I'm flipping the coin 10 times, and I'm trying to find out the probability of obtaining 5 heads. What is the probability? I can find it out from this formulation. Okay. For example, let's do it. Let's find out. This is the fact. This is the situation, right? I'm flipping a coin 3 times, and it's 3. And now I'm gonna implement this formulation. Out of 3, what's the probability of obtaining 1 heads? Probability of obtaining 1 heads times, what's the probability of obtaining heads? It is, if it is a fair coin, probability is going to be 0.5, right? So I'm going to write 0.5 to the power. How many heads do I have? 1 heads. Okay, times number of the probability of tails, again 0.5, and to the power, the rest will be, so this is heads and this is tails, okay? So the probability of heads to the power 1, this 1 and 1 are the same because I'm after obtaining 1 heads, and then the rest is going to be 2 tails, right? So n is 3, k is 1, there should be 2 here because there will be 2 tails, 1 heads, because I'm after obtaining 1 heads. Okay, you're with me, right? I'm going to ask questions right now. Once I'm finished with this introduction, now we're going to start solving the questions. So if you, what is 3 combination 1? 3 combination 1 is 3 factorial, 3 minus 1 factorial times 1 factorial. Okay, this is this times 0.5 times 0.5 squared. So it will be 0.5 to the power 3, which is 1 over 2 to the power 3, which is 1 over 2, 1 over 8, right? So what is this part? 3 factorial. I can write it like that. So 2 factorial times 1 factorial. 3 factorials will go away. 1 factorial is already 1. There will be 3 here. I'm going to multiply 3 by 1 over 8. Okay, so what did I obtain? The probability of obtaining number of heads as 1 heads, it's going to be equal to 3 over 8. So for a fair coin, we did that. But what if I had a biased coin? Then this P value will be different and 1 minus P will be different. Now I'm not flipping the coin 3 times, but 10 times, 15 times, 20 times. Okay, or I have 20 parts and only 1 out of 20 is defective. That's the general statistics. We know it from our previous experience. And I want to find out what's the probability of obtaining 1 defective parts in this 20 parts, let's say, shipment. Okay, so now that's the main idea. This is our main formulation for binomial distribution. If you remember from high school, again, you were dealing with binomial expansion. Okay, binom açılımı. Okay, you were using that in solving questions. So this n to the power n combination k you are already used to seeing this, and then this new things are coming after that. Okay, let me write once again the probability of, in binomial distribution, probability of obtaining a certain random variable at a certain number of times is going to be equal to the combination of n to k, and then probability of obtaining this this random variable k times, and probability of obtaining the other option, okay, n minus k times. So this should be the total, n and k and n minus k should be totally n, because I am flipping the coin n times. Some part of it will be failure, some part of it will be success, some part of it will be defective, some part of it will be non-defective, heads or tails. So these things will complement each other. They will totally be equal to n, and the probability of obtaining this is that. Okay, now we are ready to solve a question. I hope you understand the general idea. Now it's your time to solve this question. I want you to read the question first, write to chat, especially to me, like specifically directed to me, and then tell me the answer. Okay, guys, in this question, 1 out of 4 components will fail after the shock test, and then 3 out of 4 will survive the test. That will be the test will be successful. And using this binomial formulation, we said that we have 4 4 components to be tested. I'm interested in exactly 2 of the next 4 components to survive. And the survival probability is 3/4. The failure probability is 1/4. And I put it in the formulation and find out the result as 27/128. Okay? I'm not interested in exactly 0 point something. Just 27/128 is fine for me. Okay? Any questions here, my friends? Do you have any questions that is confusing at this point? Easy, right? So let's go to another question. Okay, it's your time again. Okay, so I am after 10 people, at least 10 people out of 15 people with this disease will survive. That means 10, 11, 12, 13, 14 people, 15 people will survive. And we said that at least 10 survive means 1 minus probability of k less than 10 is the same, at least 10, right? This part means I have no people survive, one person survive, 2 people survive, and up to 9 people survive, right? So how should I write this? It's going to be, for example, out of 15 people, no people survive times survival 0.4 to the power 0 times dying or failure, let's say 15, right? So out of 15 people, no people will survive. All of them will unfortunately die, okay? So plus I will have 15 people, but only one person. I don't know which one, any one of those. I'm going to put 0.4 to the power 1 times 0.6 to the power 14, right? So I'm going to come and write this. Out of 15, 9 people will survive, and 0.4 is the probability of survival to the power 9. 0.6 is the probability of dying, and there are 6 people left. Okay, so I can write this like that. Probability of this, like, let's say we will have k here from 0 to 9, 15 of k, and 0.4 to the power k times 0.6 to the power 15 minus k. So this is the probability of survival of people less than 10. Okay, so what is at least 10 people survive? It's going to be 1 minus probability of k less than 10. So this is probability of k less than 10. 1 minus this, at least 10. At least 10 people will survive. Did you understand this part, guys? Do you understand what I'm saying? Okay, I'm not interested in exact numbers. Again, I say we should be just focusing on the implementation of binomial distribution. I see that only a couple of people were able to send a report, send a result. Now I want you to focus on this from 3 to 5 survive. Now you can do that and tell me not the number, but like the combination and other things. So because it's like from 3 to 8, I wrote this this representation, probability of X, and the number of people who survive is between 3 and 8. And I can write it like K is equal to 3 to 8 and 15K, 0.6 to the power K, 0.4 to the power K, and 0.6 to the power 15 minus K. Okay? Or we can write it like that. K from 0 to 8 and 15K, 0.4K, 0.6, 15 minus K, minus K from 0 to 2, 15K, 0.4K, 0.6, 15 minus K. Okay, so this part is the number of people who survive, no people survive, one person survive, two people survive, and up to 8. And I'm subtracting, no people survive, one person survives, and two persons survive. So I'm left with 3, 4, 5, 6, 7, and 8 survivals, right? Do you understand, guys, this part? Do you understand that point at this time? So this notation, arkadaşlar, I will notate it like this. Binomial distribution, X is distributed according to binomial distribution, and 15 is the total number of let's say people in the group, and then I'm gonna put a semicolon here, and then I will be interested in the probability. Let's say actually it is like this. The number of people I'm interested in K, okay, and there are 15 people, and the probability is 0.4. So this is the representation of this, okay? Or we can write B binomial distributions, B, K, 15, 0.4. That means the probability of success or survival, the total number of flips, total number of people, okay? Number of people. And then this is each person, like K is 1, K is 2. That means two people, one person survives, okay? So this will be the notation that we can use for binomial distribution. B, I'm interested in K, number of people survives, and then there are 15 people in total, and the probability is 0.4. So I can write this like that. K from 0 to 8, B, K, 15, 0.4. This will be equal to this one. Okay? When you write, you can use this one. Okay, now the second is the third question. The third example is a quiz question. Okay, this will be the first quiz, only the A part. Okay, I want you to, there will be a couple of questions along the way. It is like a total thing will be a quiz, like it will be the first question of the quiz. So I'm starting the quiz right now. And I'm confident that you're not cheating, you're not sharing anything with among each other. Again, I don't need the exact number. I'm just interested in
Hocam
in
chat'e yazmak biraz uzun sürüyor da çözmekle beraber. Süreyi biraz daha extend edebilir miyiz acaba
tamam,
ya?
siz bir başlayın. Aslında çözün. Hızlıca çözebileceğiniz bir soru bu. Kolay bir soru. Endişe etmeyin. Furkan, Hayriye, good job. The trick is at least one defective item. Oğuzhan, think in terms of, okay, that's good. Yours is correct. But think in terms of even easier. Süleyman, your answer is saying you have no defective items plus one defective item. But this says will be at least one defective.
Oh,
That means
thank you.
one defective,
I
one defective, two defective, three defective, four defective until 20.
You're right hocam. I'm
Okay?
confusing. Sorry. Now it is correct hocam. I
Yes,
think.
exactly, exactly. But think again, it's not correct either. It's not correct right now. Think again. Now it says 1 minus something. Again, no plus 1. Emirhan, think once more, please. Very good. 1 minute left. Yes, yes, that's good. Think in terms of Kemal, I couldn't check your story. It's not correct. Please check it once more. Barış, good job. Enes, you shared the answer, but I'm interested in the formulation also, okay? How do you find this 0 point something? Maybe you gave it, maybe I didn't see it. That might be one. Okay, last 10 seconds. Yes, Melissa, good job. İzzetcan, why is it to the power 2? Okay, 5, 2, 3, 1. Time is up. I'm writing it right now. Okay, time is up. So let's continue arkadaşlar. So what does it say? The defective probability of defective is 0.3, right? Let's put like P is 0.03. What is 1 minus P? It is 0.97. So 0.3 means probability of defective. This is probability of non-defective, right? So it says will be at least one defective. You can write either like at least one defective from 1 to 20, binomial distribution. I'm interested in K. Totally there are 20 items, and the probability of having a defective one is 0.03. Okay? Or you can say 1 minus probability of obtaining no defective, right? What is probability of obtaining no defective? Out of 20 parts, components, none of them will be defective. The defective probability is 0 to the power 0, 0.97 to the power 20, right? So I'm going to say 1 minus 20 combination of 0, 20 to 0, 0.03 to the power 20, 0.97 to the power 20. So this is 1, this is 1, and this is left. So my answer will be 1 minus 0.97 to the power 20. Okay? So if we give if we give the number, there will be 0.4562, okay, or somewhere around 0.46. Okay, does that make sense, guys? Everybody is with me. We understood what's binomial distribution in general, and then we will go to the next part. But let's think about this B part again. Now I want you to read part B, and then once part B is over, we're going to go to a new distribution. Before that, we will have a break of 10 minutes, okay? Now I want you to focus on part B. What does it say? Suppose that the retailer, perakendeci, retailer receives 10 shipments in a month, and the inspector randomly tests 20 devices per shipment. 10 shipments. Shipment means cargo, okay? 20 shipments, and the person tests 20 devices per shipment. What's the probability that there will be exactly 3 shipments, each containing at least one defective device? There will be exactly 3 shipments out of these 10 shipments, each containing at least one defective device. Okay? There are 10 shipments, shipment 1, shipment 2, up to 10 shipments. And then I will have 20 devices here, 20 devices here, and so on. And I will say only 3 of them will have at least one defective. How can you solve this question?
We will use 2 times binomial hocam.
3 times, right? There are 3 shipments. We will use the binomial couple of times. At least I should say that. So we know the probability of obtaining at least one defective out of 20. Okay, there is at least one defective, probability of obtaining at least one defective, out of 20 devices, right? I have 10 shipments, and I'm interested in 3 of them having one defective, at least one defective. Barış, how did you solve, my friend? Barış İnce.
Hocam, there is 10 shipments.
10
So
shipments.
at least, it says at least 3 of them. So 10 to 3 combinations.
It's not at
Exactly,
least
sorry,
exactly.
Exactly
Okay.
3 shipments. At least 3. So hocam,
Okay.
then if we found from the previous part 0.46. Yeah,
0.46 being the probability of obtaining at least one defective, right? Very nice.
Yes, hocam.
So there
So
will
it's,
be to the power 3 times
0.54
0.54 to the power
to the power 7.
7, right? Very nice. So this is the probability of obtaining at least one defective, okay? One defective out of 20. So this is something we found in the previous part. And I'm interested in out of 10 shipments, 3 shipments, exactly 3 shipments having at least one defective times the others having no defect. Okay, 7. 3 of them will have this, 7 of them will have that. So this is the probability of the second part. Okay, you see, I am using one binomial, and then using this outcome of that binomial, I'm using it again for the next binomial. Okay, is that clear, guys? I can see that Mustafa, Hayriye were able to come up with answers, but Hayriye, you should work on it a little bit more. Mustafa has done a good job. Thank you, Mustafa. Barış, like I got 3 answers, but did everyone
Can we see the
understand this part?
question again? Hocam,
Sure.
can we see the question?
Sure. So that's the question. 10 shipments in a month. The inspector randomly tests 20 devices per shipment. What's the probability that there will be exactly 3 shipments, each containing at least one defective device among the 20 that are selected and tested from the shipment? This time, I have 20 shipments, and shipments have a kind of probability of having at least one defective. In the previous one, I have 20 items, and out of these 20 items, I have at least one defective item. Okay? So that's something that you should be careful about. Let's have a break of 10 minutes. After that, if you have questions about this question, we can continue. Let's have a break and get some rest, and then meet around 10 o'clock. Okay? See you, inshallah. 10. So now I'm going to start discussing about geometric distribution. We talked about Bernoulli. Okay? Bernoulli distribution. It was like pass-fail, or male-female, or success-failure, defective, non-defective. Okay, it was a general process, and it's the basis of many distributions here. Then we went into the binomial distribution. It has a specific type, and we are trying to find out of n, let's say, out of n occurrences, I'm interested in like k occurrences of something. Let's say out of 20 items, 1 defective. Out of 15 people, 10 being 10 surviving. Okay, out of 100 students, 10 getting failure, or 10 getting a success grade. Okay, so all of this is like binomial context. But now in geometric distribution, I will have like observations until the first heads. Okay, so I'm tossing a coin, tails, tossing a coin, tails, tossing a coin, heads. Okay, what do I say? How many tosses did I have? 3 tosses. So this number 3 will be the random variable for my geometric distribution random variable. Okay, I toss the coin until I observe the first head. I check people who are entering the classroom until I observe a female. Okay, I go to a shop and I check the items and until I see a defective item, or until I see a laptop, there are this many devices on the shelf. So there are many contexts, and we will solve questions together in that context. Okay, so here I toss the coin until I observe the first set. So X is going to be the random variable, total number of coin tosses. Okay, so I'm flipping the coin, tails, tails, tails, heads. What's the random variable? 4, because I flipped it once, twice, 3 times, and 4th times, and I got it 4th time. So my random variable X will be 4. Okay, I got it tails, heads. Now it's going to be 2, because I got it in the second flip. Okay, male, male, male, male, female. So I was searching for the female, and it is now the 5th person. Okay, it was normal, normal, normal, normal, normal, normal, normal, and diseased person. So I'm trying to find out when the diseased person enters something, when the diseased person is detected. 1, 2, 3, 4, 5, 6, 7, 8. So X is 8 here. Okay, so that's why we call it X is distributed according to geometric distribution, and is the total number of tosses. Okay, total number of tosses, and then P will be the probability of obtaining heads, probability of obtaining female, probability of obtaining diseased person. Okay, so this P is something like that. How would you write the formulation, guys, for this probability of X and let's say n tosses? How do you write the probability? Can you write the probability of this geometric distribution? Probability distribution function, let's say. It's going to be a probability distribution function with respect to n and p. What is my... Are you there, guys? Do you hear me?
Yes, hocam.
Yes, okay. Is the question understood? How can I write the px of n? The probability of obtaining p and probability of obtaining like heads, probability of obtaining heads, and probability of obtaining tails. What should I write here? It's going to be 1, and the other one is going to be n minus 1, right? So there will be n minus 1 tails and only one heads. This is the latest, the final outcome. Okay, if I want to change it, if I want to write it, like again, probability of heads, but before that I have n-1 tails or n-1 males. Let's say the probability of obtaining males is 0.7, 0.3 is the probability of obtaining 3 in a classroom in engineering. So you would say I have 0.7 probability, and I have 1, 2, 3, 4 times 0.3, right? So this is like non-female, let's say male students, and this is going to be the female student. What's the probability here? Obtaining the female student as the 5th student, okay? Px of 5. Obtaining the probability of obtaining the female student coming 5th, exactly 5th to the class. Is red better than blue, or blue was better? What do you think, guys?
Blue hocam.
Blue is better, right? Red is a little bit pale. I didn't like it. Maybe I can find more like dark thing here. Okay, is this clear, guys? Let us go to the first example. So this is example 4. For a certain manufacturing process, it is known that on the average, 1 in every 100 items is defective. What's the probability that 5th item inspected is the first defective item found? So I'm looking for your answers at this point. Okay, guys, so the question says the probability of obtaining a defective item is 1 out of 100. What's the probability that the 5th item inspected is the first defective item? So the probability of obtaining a defective item is 0.01, 1 in every 100. And I have a non-defective probability. Obtaining a non-defective item is 0.99. And I'm going to see 4 items as non-defective. Okay. And this is defective. I'm going to see first 4 items. And then the 5th item will be the defective item, right? So this is the probability of obtaining as the 5th item, defective item as the 5th item. Okay, is that clear? Easy, right? I guess. Yes, let's move on to the next question. Yes.
Where is the distribution?
The distribution.
This is just probability.
This is probability. If I want to write a general thing, this is the distribution. Okay, probability of k, the 1 minus p to the power k times p, k minus 1. This is the probability distribution. Okay, for different p's. Okay, geometric distribution for different p values, obtaining a defective, obtaining a healthy person, obtaining a female person, p, and I want to find out at which instance will this occur. Okay, that's the probability distribution. If you want to plot this, for example, for this purpose, 0.01, if I want to have it is in the first item, it's going to be 0.01. If I want to have it as the second item, it's going to be 0.01 times 0.99, right? So it will be 0.99 times 0.01. It will be somewhere here again. it will be 0.0099. The previous one was 0.01. So very close to each other. So then 0.01 as the third item. I'm gonna do this. So this is gonna be my distribution, okay? So this whole thing gives me the distribution. From the distribution, I can find the probability. So that's the trick. From the distributions, it has a formulation, and from that formulation, I can find the probability of obtaining a certain sequence, a certain point, okay, in the distribution. Is that clear, Berke?
Yes, hocam.
So I have a distribution, but I'm using this distribution, this formulation to calculate probabilities, which we did, for example, here, right? I know it's the binomial distribution, and we were trying to find out the probabilities. Okay, from the distribution, I can find the probabilities. So that's how it works in this distribution concept, spatial distribution of discrete random variables. We are gonna calculate probabilities. In next time when we meet, we are gonna calculate the mean expected value or the variance of the distributions. Okay, these are coming afterwards, but this is like a general idea. I have a formulation that describes this random experiment with a certain mathematical explanation. Using that distribution, now I can find out probabilities. So I have a PMF. Okay, I have a PMF like this, and from this PMF, which will change for every p-value, you know, when this p-value and k-value changes, this whole process will change with respect to the p-value, and in general, like geometric distribution, p-value will be the main idea. So it will all be dependent on this PMF, and then from this PMF, I can calculate the specific probability. Okay, so let's go to the next question. Okay, guys, it's your time to check that. Let me read the question carefully for you. At a busy time, a telephone exchange is very near capacity. Telephone exchange means, let's say there is a circuitry in the telecom building, and then there are calls coming and going, but sometimes, you know, you cannot reach because the lines are busy. You see, you know, that's what it's explained here. It's very near capacity, so callers have difficulty placing their calls. It may be of interest to know the number of attempts necessary in order to make a connection. So I call once, I cannot connect. I call twice, I cannot connect. I call again, and I connect. So my random variable will be 3. I'm placing a call, and I'm trying to find out after how many attempts I can connect to the person who I am calling. Okay, is that clear, guys? Number of attempts necessary in order to make a connection, just like obtaining heads after so many attempts. Okay, suppose that we let p is being 0.05 being the probability of a connection during a busy time. So I will make 100 attempts, and only 5 of them will connect. Okay, that's the usual thing for a busy time telephone exchange situation. So the probability is 0.05. We are interested in knowing the probability that 3 attempts are necessary for a successful call. So once I was reading the question, many of you were able to send me the answer exactly. So how many attempts will be unsuccessful 2 attempts, right? So what is 1 minus P? 0.95 unsuccessful attempts. Placing a call with an unsuccessful attempt. The probability of obtaining an unsuccessful attempt. So it will be 1 minus P to the power. If I say 3 attempts, I should be able to connect. Then I will write 2 here times P to the power 1. These two, when I add these two, I should get 3. Okay, so the probability is 0.95 to the power 2 times 0.0105. What is the answer? Let me check my notes. It's gonna be I changed the numbers, so I cannot tell you exactly. If you have any calculators, that will be good, but I don't need that thing right now. So is this clear, right? Geometric distribution is easy, but just you have to understand that it is a geometric distribution. That's the only trick that you're gonna have in geometric distribution. Okay? Read the question, understand it's talking about geometric distribution, and then perform your calculations. Okay, here is another type of distribution, which is called Pascal distribution or negative binomial. I will have a random experiment or repeated independent trials until observing m successes. Okay, now, for example, I will have 10 flips of a coin, and I'm gonna be after 3 being heads. Okay, like 10 flips of a coin, and I am after only like what is until I observe. I'm not doing this 10. I am flipping a coin until I see 3 heads. Okay, flip a coin, see what it is. Heads. Okay, count 1. Flip a coin, tails. It's not. Don't count. But the total count becomes 2. Flip a coin, tails. Flip, the total count is 3, but the number of heads is 1. Okay, that's how you do it. Repeat the random experiment until you observe m successes. Okay, that's the main idea. What is the random variable? Total number of coin tosses in this experiment. Okay, how many times should I flip the coin until I observe 3 heads? Okay, that's why this will be like 3 heads, and the probability will be, let's say it's a biased coin, and obtaining heads is 0.3. So I'm gonna solve the question according to the Pascal distribution. Okay, so for the Pascal distribution, here is the formulation. Okay, I explained this in the video, like k minus 1, combination of k minus 1, m minus 1, p to the power m, and 1 minus p to the power k minus m. Okay, k being m plus 1, m plus 2. Like k being, let's say, you want to have 3 heads, right? And how many flips you can have? You can have 3 flips, 4 flips, 5 flips, 6 flips, and many flips until you reach 3 heads, right? So that's why, like, it can be 3, 4, 5, 6, and so on. So what is k here? I will have the number of k will be number of flips I should make to obtain m heads. Okay, and m is the number of heads I'm aiming for. Okay, so this is p obtaining heads, probability of Probability of obtaining heads, probability of heads. And then this is probability of tails. M is again, do you understand this formulation, guys? It's a little bit tricky. You say that, for example, you want to obtain 3 heads, and you are now in the 5th flip, okay? You are now in the 5th flip. So it's the K is 5. What did you get? Until now, you have 4 flips, and 2 of them were heads. You know, I'm trying to find out K being equal to 5. Okay, what does it mean K being equal to 5? I'm gonna reach to the 3 heads count of number of heads being 3 in the 5th flip. Okay, I'm gonna reach 3 heads in the 5th flip. So before that, I had 4 flips, and 2 of them were heads. And we said that the probability is 0.3 for obtaining heads. I'm going to say 0.3. And in the final situation, how many heads will I have? 3 heads. How many tails will I have? Out of 5 flips, I'm going to have 2 tails, right? Now I'm going to write 2 here. So this is the probability of heads, this is the probability of tails, and I'm going to have, in the final situation, because I'm after 3 heads, in the final situation, it will be 0.3 times to the power 3. 3 heads, probability of obtaining 3 heads, and probability of obtaining 2 tails, because out of 5, I'm going to get 2 tails, 3 heads. But here's the trick. I need to find out this part, which is like 5 minus 1, okay? Just before I flip the coin 5th time, because I'm aiming for the 3rd head coming as the 5th, in the 5th flip. And this is like, I'm aiming for 3 heads, so 3 heads minus 1, okay? I hope you understood what's going on here. So this is like number of heads you are aiming for, 3. And you are like, you have 5 flips and 3 of them are heads. And I am left with 2 tails. Okay. So let's start with a question and see how we do it. In an NBA championship series, the team that wins 4 games out of 7 is the winner. You know that, right? It's a playoff or champions something. Suppose that teams A and B face each other in the championship games, and that team A has probability of 0.55 winning the game over team B. Okay, what's the probability that team A will win the series in 6 games? So there are possibly 7 games, and some team has to win in out of like 4 games out of 7. So the probability of team A winning the series in 6 games, not going to the 7th game. The series should end at 6th game. Okay. Now I want you to focus on this and give me the answer, please. This part. 3 games were won by team A so far, and 2 games were won by team B so far, right? And this team A will win the last game, so that like 6th game, team A will win. so that they will reach to 4 wins and series will be over. Is that clear, guys? Is that clear right now? The team A will win 3 games so far. Team B will gain 2 games so far. And in the 6th game, this team A will win, and so that they will reach to 4 out of 7 or 4 out of 6 or 4 out of 5, 4 out of 4. Like, it doesn't have to end, it doesn't have to go to until 7th game, right? You can finish it earlier. You can win 4 out of 4, and then you're gonna win the series. Is this clear, my friends? So, as many of you pointed out, it should be, what is K here? My friends, what is K?
Isn't it 6 hocam?
6, exactly. 6 is K. What is M?
4.
4. Okay. Out of 6 games, I need to win 4 games. Okay. What's the probability of team A winning the game? 0.55. It's given here. And probability of losing the game for team A is 0.45. Now I'm going to apply this formulation, Pascal distribution. Probability of obtaining 6 out of 4 with a probability of 0.55 will be equal to K minus 1, 5. Out of 5 games, I need to win 3 games. Team A won 3 games. And for winning 3 games, now I'm going to write, now finally I will have 4 games to win. And then the other team, they're also a good team, and they need to win 2 times, right? Out of 6 games, team A will win 4 games. And team B will win 2 games. Okay, that's the main idea here. Does this make sense, my friends? Okay. So that was Pascal distribution, and I was trying to find out like how many times, like I know that it should end this time, but until obtaining certain number of heads, until obtaining certain number of female coming into the group. Okay. Now I want you to focus on this question. What's the probability that team A will win the series? What's the probability that team A will win the series? It's an independent question right now. What's the probability of the team A will win the series? They will win either in the 4th game, 4-0, right? So there will be 4-0. Team A will win 4 times. Team B will win 0 times. I can win it in the 5th time, and I can win, like team A will win 4 times, and team B will win 1 time. And I can win at the 6th game. I can win again 4 and lose 2. And 7th game, I can win 7-4 and lose 3. Right? And for each of these, I can write the probabilities, right? How can I write the probability for this one? 4th I'm winning the team A winning the game, the series in the fourth game. How can I write it? Out of 4, you won 3 games so far. 3 out of 3 games. And winning probability is 0.55. And you're going to win 4 times. Team B will win no time. Okay, will not win until that point. Okay, if you come here, again, this is now 5th game. So you, after, until 4 games, you won 3 of them, because the last one will be the winning game, okay? The last one will be the winning game. So again, I will write 0.55, and I will win 4, but lose in 1. Is that clear, guys? For this one, I'm gonna have, this is 6th game, so until that point, I played 5 games and won 3 of them, and then totally I will be winning 4 and losing 2. And the last one, out of 6 games, again, team A will win 3 of them, and finally they will be winning 4 of the games, and the other team will win 3 of the games. Okay, so that means I will add all these up to find the probability that team A will win the series. Okay, this plus this plus this plus this will be the answer. Did you understand what I did, arkadaşlar?
Yes hocam.
Exactly. Probability, Emmanuel says, the sum of 4th, 5th, and 6th probability. We should also include 7th probability, arkadaşlar, okay? So out of 7 games, the team A will win 4 and will lose 3 of the games. So that is also possible. Okay, so it's a kind of play. Yes.
Can we write this as an equation of sigma?
Yes, exactly. You can write it. Let's write it together. So it will be like K going from 4 to 7. Okay, winning the game in the 4th match, winning the series in the 4th game and 7th game, and I'm gonna write here K minus 1, M minus 1, again 0.55. I know what M is. M should be always 4 minus 1, and I'm gonna write 4 here times 0.45 to the power, and totally I will have K minus 4, right? So for example, here K is 5, K is this one, and this is 4, this is K minus 4, right? So you can write the probability like that. Is this clear? As a formulation, you can write it like this, or even like K minus 1, 3, and then 0.55 to the power 4, 0.45 to the power K minus 4. The K's will be from 4 to 7. You can write a simple code and have this calculated. So this question is also okay, I guess. I'm gonna go to the last part. We have almost 20 minutes, and I want to focus on the Poisson distribution. We will have one more quiz question today about Poisson right now. So Poisson is highly is a distribution which you can see in many places. Okay, in discrete as a discrete random variable distribution. So Poisson, this is read as Poisson. Okay, it's not Poison, it's Poisson. It's a French mathematician's name. It means fish. Okay, in French, Poisson means fish. Poison means, zehir. So it's not the same thing. So Poisson is fish. We are counting the occurrences of certain events in an interval of time or space. For example, number of people entering the shop, number of cars passing by, number of particles hitting the sensor, number of something in a certain space, like number of rocks falling down to a certain area. Okay, these are like counting occurrences. Okay, we are counting occurrences, but it has to be in a specific time or space, in a certain space or certain time interval. Okay, so we say that my random variable is distributed according to the Poisson distribution, and lambda is my parameter, which will be coming from my previous experience. For example, in the previous question, what did we say? We know that from the previous games, team has won 55% of the matches, right? So other matches, other games were on the favor of team A, but team B won 45 of the 100 games. So we know it from previous experience. The probability is coming from the previous experience. Here in Poisson distribution, this lambda is coming from our previous experience. Okay, we know it, how many times, how many people enter this shop in this certain time period on average. But we don't know that this will happen exactly in this time period. For example, normally I know that, let's say 10 people enter the shop in Kayseri Forum in 1 hour, let's say, in 1 hour. But I'm trying to find out what's the probability of obtaining 3 people in this 1 hour interval. What's the probability of having 20 people? What's the probability of obtaining 5 people? Okay, so these are some tricks that we need to be aware of. And here is the probability distribution function, probability distribution formulation. It's going to be e to the power minus lambda. This lambda is the average number of events. And I'm going to multiply it with y lambda to the power k. K will be like, I will be interested in 20 people coming to the shop, okay? 20 people in the shop. Normally, on average, in 1 hour, on average, it is 10. But I'm trying to find out what's the probability of obtaining or having 20 people in the shop in that 1 hour period. And divide by, okay, k factorial. That's what mathematicians found out the probability for this kind of distribution. Okay, e to the power minus lambda times lambda to the power k divided by k factorial. Again, k is the number of occurrences that we want to find out at this point in time, but we know this lambda from our previous experience as an average occurrence, and then this lambda will be used in 2 places, lambda to the power k, e to the power minus lambda and k will be used here and here. Okay, so let's start with, I'm going to solve 3 questions here, guys. Let's start with this simple question. Let me write the formulation once again. E to the power minus lambda times lambda to the power k divided by k factorial. Okay, e to the power minus lambda, lambda to the power k divided by k factorial. So in this question, you're going to find out what is k and what is lambda, and use this formulation, probability of obtaining k something particles here, and then you're going to use this to the power lambda to the power k divided by k factorial. So during a laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. So what's the time interval? Time interval 1 millisecond. Okay. What is the average number of radioactive particles? It is 4. Average number of particles. So what is this for? What is this for, guys? 4 is going to be lambda, right? 4 is lambda. So I'm going to write 4 here. So while you are solving the question, you need to find out what is lambda first. Okay? Then you go to the formulation and find out what is the probability that 6 particles enter the counter in a given millisecond. So now I want to find out 6 particles. So 6 particles. On average, it is 4, but I'm trying to find out what's the probability of obtaining 6 particles. Not 4, but 6 this time. Okay? Is that clear, guys? So easy. I'm going to put like k equals 6. It's going to be equal to e to the power minus 4 times 4 to the power 6 divided by 6 factorial. That's the answer. Is that clear? Any questions? I don't need you to calculate any further at this point, but that's enough. But this is how we approach the problem. This is the easiest, the most easy question that you will get. So, but what is the trick here? The trick is you need to find out lambda here, okay? What is lambda? How can I find lambda? You should be searching for the answer to that question. Again, what is k? What is this guy asking me? How many people? How many particles? How many cars? How many this? How many that? Okay? So this k will be 6. How about if I have at least one particles, if I say at least 1 particles in a given millisecond, at least 1 particles, how do I write it? It's going to be a summation, right? It's going to be summation of k from 1 to infinity e to the power minus 4 times 4 to the power k divided by k factorial. At least 1 particle. Or there is another way of doing this. Probability is 1 minus obtaining no particles. E to the power minus 4 times 4 to the power 0 divided by 0 factorial. 0 factorial is 1. So this is 1. This is 1. So it's going to be 1 minus e to the power minus 4. Is the probability that I will get at least one particles. Okay, so it's a huge probability. It's like almost 99.9%.
Hocam,
Yes,
can you repeat the last part? Please.
sure. Let me go to this this part. Okay, I am asking, give me the probability of like at least one particle, what's the question? Passing through a counter. Okay, counter sayaç, radioactive particle counter. At least one particle passes through the counter. Okay, what's the probability of at least one particle passing through the counter? How can I do that? I can say there will be, if I have one particle, okay, one particle, what will I say? Probability of k equal to 1 and e to the power lambda is always 4. I know that. It's a historical data. I know that. It's going to be e to the power minus 4 times 4 again here, lambda to the power k. It's 1 divided by 1 factorial. So this is one particle. Okay? The probability of obtaining one particle. Probability of obtaining two particles, e to the power minus 4 times 4 to the power 2 divided by 2 factorial. And so on. What was my question? At least one particle. I can write this. I'm going to add from 1 to infinity all possible options. I'm going to say e to the power minus 4 times 4 to the power k divided by k factorial will be the probability of obtaining at least one particle passing through the counter. Or I can say one probability is going to be 1 minus no particles. Okay? So at least one particle means 1 minus no particles. What is the probability of obtaining no particles? Here I'm going to put e to the power minus 4 times 4 to the power 0. No particles. K is equal to 0. Divided by 0 factorial. K is equal to 0. K is equal to 0. No particles. Is that clear right now, guys?
Clear, hocam. Thanks.
Okay. So let's move on to the next question. Now it's your time to solve it. Totally 15 tankers can be handled in one day, but on average 10 tankers are coming to the port. Okay, port is Rıhtım. Okay, it's like oil tankers are coming, and then tanker, you know, tanker ship, big ships are coming to the port, and then people can handle means you can deal with or solve their needs accordingly. Okay, and then what's the probability that on a given day tankers have to be turned away? So that's the tricky part. What's the probability that on a given day have to be turned away? What is lambda here, guys? What is lambda?
Hocam, isn't it 10?
Lambda is 10, right? 10 is the average number of oil tankers. What is being asked? What is the question? Probability of X being more than 15, right? That's the question. Probability of number of tankers, oil tankers being more than 15, because they can only handle 15 tankers per day. So doesn't it mean 1 minus probability of x less than 15, less than or equal to 15. Are you following me? Is that okay? Are you following me, guys? So how can I write this probability of x being less than 15, less than or equal to 15? So what does it mean? It's going to be probability of x being equal to no tankers coming, one tanker coming, two tankers coming, and up until 15 tankers coming, right? So this is like, it is possible to have all tankers to be handled in one day. If I subtract 1 from this value, I'm going to get the probability of tankers being above 15, like 16 tankers will come, 17 tankers will come, and some of them will have to be turned away. So they have to leave. They cannot be handled. So I can also say that it's like k from 0 to 15 e to the power minus 10 times 10 to the power k divided by k factorial. 1 minus this will be the probability of obtaining tankers more than 15. Is this clear, guys? Okay, so it is 1 minus 0.9513, and it is like 0.04787. Okay, the last question will be the quiz question right now. This is going to be the quiz question. You will have 5 minutes to solve it.
Hocam,
Quiz
both of them or
question.
just
Just this A part, okay? I need just A part. Let me read the question. In a certain industrial facility, accidents occur infrequently. It is known that the probability of an accident on a given day is 0.005, and accidents are independent of each other. What's the probability that in any given period of 400 days, there will be an accident on one day? What's the probability that in any given period of 400 days, so my interval is 400 days. That's the trick of this question, arkadaşlar. Please be careful. That's the trick of the question. What's the probability that in any given period of 400 days? So I'm looking at 400 days, okay? What's the probability that there will be an accident on one day? Only one experiment, okay? One accident. In the first day or second day or 400th day, but there will be one accident. What's the probability of having one accident in 400 days? Okay, the time started. It's going to end at a little bit over. So you have 3-4 minutes.